Hello everybody, this is Dr. Andrew Chrysler, teaching electromagnetics at Idaho State University. In this video, I'm going to summarize and compare several topics which are in almost every undergraduate electrical engineering electromagnetics textbooks. And those topics are waves, wave equations, transmission lines, and plane waves. Most likely, whatever textbook you're using has a chapter on each section of this. They have a wave introduction, a transmission line chapter, and a plane wave. They're all quite similar and related, but if you have been going through the course over a semester, it might be difficult to see how to put all those pieces together. In this video, I'm going to try to do this for you. So first, let's take a look and know that we have this differential equation. This differential equation may look similar to you because you saw it developed in wave equations from Maxwell's and on transmission lines. And it's very similar to another equation that's so common. It has this name called the Helmholtz equation. Now, from your differential equations class, what you should know is that this type of differential equation has a solution that's shown on the bottom. And there is two parts to that solution. There is a first part, which we consider to be the forward traveling part, and the second part, which we consider to be the reverse traveling. And we denote the reverse with the minus, the forward with the plus, and we see that the forward traveling wave has a minus in the exponent, whereas the reverse one has a plus in the exponent. Now, when we see this solution, we should know that these coefficients, which are determined from boundary conditions, they could be real or they could be complex. If they're complex, those coefficients would take these forms, where we have the magnitude and then an angle. So we should know that those coefficients, each one of these, could be a real number or it could be a complex number. And then we should also know that this number, this constant gamma, which is up in the exponent, could also be a complex number, which we usually write in the rectangular format as alpha plus j beta. So the solution to this now, has two parts, and we often prefer to simplify this, like many things in engineering. We prefer to simplify it, and we do that by assuming that we have just a forward wave. If we do that, basically what we're saying is, due to boundary conditions or real-world ideas, etc., we're saying that this coefficient would go to 0, leaving us with just one part of the solution, which is the forward wave only. Now, we can see that because this could be written as the e to the x, e to the alpha plus j beta, we may prefer to write our solution as a series of e to the exponents. And those exponents come from several things, right? This exponent, this one comes from the angle that's possible in your coefficient, that's from the boundary condition. This one is the real part of our gamma constant, and this is the imaginary part of our gamma constant. And so we can rewrite this as this multiplication of these exponents. Now, why would we do that? Well, it's because in electromagnetics and electrical engineering, we really like to be able to go back and forth between the phasor domain and the instantaneous form. And the instantaneous form is really easy to see or determine how you're going to write the instantaneous form when we write it using this exponent notation, using this Euler formula. So when we rewrite this in the instantaneous form, we're taking the real part of all of this, and what I've done here is I've separated the real part, so the coefficient magnitude would be real, and then this e to the alpha would also be real, whereas these are all imaginary. And from our study of phasors, which is something that you probably studied early in your electrical engineering career, right? We know that these imaginary parts are going to go into a wave, whereas the real parts are going to end up as the amplitude of that wave. So for this reason, we like to write the solution to those differential equations like this, so that we can easily go back and forth between the phasor and this time domain form, the instantaneous form. And when we've written it this way, we can quickly see that these are what's going to be inside of the cosine, whereas these are going to be inside of the cosine, whereas these are going to be out front in the amplitude since they're real. Now, when we have that instantaneous form, what we should notice is that there is an alpha, and we can see that if this alpha is larger than 0, that's going to make this amplitude get smaller as the z increases. So the larger z gets, we can see that this term is going to get smaller. It's making us lose the amplitude, right? It's making us lose the amplitude that's out in front of that cosine wave. And so we often prefer to find a case where alpha is equal to 0, which we call a lossless case. And so in the lossless case, we're able to eliminate this exponent part. Usually you need to go into more complex electromagnetics topics in order to deal with alpha being greater than 0. And then if you want, it is also possible for alpha to be less than 0, but this is also another very complex case where maybe you're dealing with something like lasers or active devices. So because of this reason, we like to deal with the lossless case, and we see that the lossless is really just meaning that we're not losing amplitude, right? Our amplitude is going to be constant. And we've denoted that, we've made that clear by showing that this is not a function of z, right? We've completely eliminated that, and this is just a single magnitude. Now, this should go back, and we should relate this and realize that the phasor differential equation often has this instantaneous solution. And so from that, now what you should start to realize is that when you studied waves, and we put them into this, what we called a standard form, the standard form is very closely related to this specific differential equation or wave equation. And that kind of back and forth relationship comes up a lot in transmission lines and plane waves. And so this instantaneous solution for the forward traveling wave only of that phasor differential equation is exactly the same as probably this standard cosine wave, which you learned about phasors with. And so that's one of the ways, connections that I want you to make, is that differential equation comes up a lot, has this specific instantaneous solution, which is the same as a standard cosine wave, which you learned phasors with. So those standard cosine waves can usually be written in a couple different ways. And the time domain, the time related part, we may write in this radial frequency, and we may come up with this phase constant and then our reference phase here. These are equivalent ways of writing the same thing. However, it leads us to these a series of equations or relationships that you often see in your textbooks, which are basically ways of relating the velocity of propagation, this wavelength, and this beta, and this frequency. Now, if you go into more complex upper division, graduate level electromagnetics, some of these may break down a little bit, but for what our purposes, plane waves and transmission lines, these are going to hold true. And basically, we're considering what we call the non-dispersive case. So now let's derive the transmission line and the plane wave equations in parallel. So first, we start with the telegrapher equation and the Maxwell's equations. And what you should note from this is that these are kind of mixed, right? In the telegrapher equation, we have on one side voltage, the other side current, whereas in these Maxwell equations, which we're stating are in source-free environment, and that source-free nature came from these. And we can see that they're kind of mixed as well, with the E field on one side and the H field on the other. Then from these two equations, what we do is we do some substitution of this using these two equations simultaneously, so that we can get to these wave equations where we're able to arrive at a single equation that's only E or only H, and likewise only V or only I. So that's the point of getting to this wave equation. And we should already start to see and remember that these wave equations, right, they're closely related to that standard cosine waveform. And that's another connection that you should make, is that we can start from telegrapher's equations or Maxwell's equations, and we can derive these wave equations, which are closely related to those standard waves, which we like to look at for phasors and instantaneous domain. So now what we do for the transmission line is we select the voltage to further derive, and in the plane wave we select the electric field, which we continue to derive. For the transmission line, we don't need to do anything further, right? We just select the voltage as the one that we're going to look for the solution. However, for the plane wave, we make a couple more assumptions. And that's basically related to the fact that the transmission line is scalar, but the plane wave, we're dealing with vector components. So in order to reduce to a scalar equation which you can see are very similar, what we do for the electric field is we assume a uniform plane wave. So we take, in our case, we used the xy plane, and we imagine that the electric field would be the same everywhere. And then we imagine not only is the electric field the same everywhere on that plane, we said that in the most simple case, the electric field would be pointed in just one direction, which we said would be the x direction. And upon doing that, we were able to make this simplification where we were able to reduce this vector equation down into this same differential equation in a scalar form, where we're going to solve it for just one directional component only, just that one e to the x. And so instead of dealing with it as a vector with the x hat, we're just dealing with this part of it. So from there, right, we can see that these two equations are extremely similar. In fact, they even have that same gamma constant. And we know that the solutions are going to be the same. Okay, so we have a forward traveling wave and a backward traveling wave for each. Now from here, I'm going to make a couple simplifications. On the transmission line case, we're going to assume that we have a no reflection case. So we spent some time in transmission lines looking at what would happen if you had no reflections, or reflections or no reflections. But in order to compare this to the plane wave, let's assume that we have a no reflection case for the transmission line. And then for the plane wave, let's basically assume that the plane wave is started somewhere and is propagating very long ways out to infinity, and therefore there's really going to be no reverse traveling wave. And so the plane wave case, we assume the physical meaning is only forward traveling, and we'll compare it to the no reflection case of the transmission line. So once we have this, we can once again see that the transmission line and the plane wave case look identical, basically. And the only difference is this gamma constant. Now for the transmission line, we derived it from an RLGC circuit model, whereas for the plane wave, this came about from the Maxwell's equations. Let's make a couple more assumptions, because like we mentioned previously in this video, we like dealing with the lossless case. And in that lossless case, we should be able to simplify this a bit. So we should be able to go from the gamma squared to gamma, and then we should be able to simplify for the lossless case. For the lossless case on the transmission line, we said that the transmission line, the metal parts would be highly conductive, and so that this resistor would go away, and it would have a perfect insulation, so that we don't have any conductivity between these two lines. Okay, so for the transmission line case, we set R to 0 and G prime to 0. And then for the plane wave case, we say that the plane wave is propagating in a zero conductivity environment. Now, what that does for us, basically, is going to get rid of the parts of this that added to the loss, that added to that alpha that made the amplitude of a instantaneous wave reduce. Okay, so this reduces our gamma on the left-hand side for the transmission line to j omega L prime C prime root, and on the plane wave to j omega root of mu epsilon. Okay, so now we have a relationship for gamma, and it's slightly different between these two, because on the transmission line, we derived this using that RLGC model, and on this one, we started from the Maxwell's equations. Okay, so this is what these two differences come from. And we still, though, like to continue to compare these two cases by saying that the gamma should be equal to that real part plus the imaginary part. And so for the transmission line and the plane wave, when we assumed the lossless case, our gamma reduced down to just an imaginary part. And because of that, we can see that if gamma is equal to alpha to j beta, this beta term will be the non-j component of our gamma. And so for this reason, we come up with a beta term for both the transmission line and the plane wave, and they look very similar. There's a couple things that we need to note now. One is that for the lossless transmission line, we say that L prime C prime is going to be equivalent to mu epsilon. So that's where this came from. In your textbook, it probably just stated this as something you should no or was true. And this is basically where it comes from. We can see that now. And then for the plane wave case, and I want to mention another thing, which is that we have assumed a fairly simple model for the materials that we're dealing with. We've assumed pretty simple models for how the mu and epsilon vary with frequency. And if you take a graduate level course or go beyond, the relationships can get pretty complicated, and it will break down this beta is equal to k. And so we only have this only for TEM. And because of that, this is why on the plane wave case, we like to use k instead of beta. And that's because we know that there are much more complicated cases that you could deal with where that relationship breaks down. So on the transmission line side, your textbook may continue to use beta, but for the plane wave side, we like to use a k, a wave number, where we are basically saying that there's a more complex relationship, and that only under this one circumstance would beta be equal to k. Now, from here, we should note that we have the solution for our forward traveling wave. We now have reduced our gamma right to beta for transmission line, and gamma went to k for the plane wave, and this is because we made these lossless assumptions. And both sides have a coefficient. And just like in the first part of this video, we knew that the coefficient could be complex, could have a magnitude and an angle, and both the voltage and the electric field could do this. And so we'll write them like this. Now, doing that, it makes a lot of sense, because this once again helps us to go back and forth between phasor, right? This is a phasor, and I've denoted this with a tilde, to the instantaneous form. We can see that these parts are all j to the something, so they're going to be inside of the cosine term. And likewise for the plane wave, we see the same thing. And the coefficient, right, is not a function of z, and so it's not going to be getting smaller as z changes. And this is because we're dealing with the lossless case. So going from the phasor to the instantaneous form, we can now see that the voltage and the electric field look very similar. We will continue to write the voltage as a scalar form, but the electric field, we may revert it back to the vector form. And that makes sense because our original equation, right, was in the vector form. And so for the electric field, it makes sense to revert this or keep our knowledge of the fact that it was a vector-based equation and that we solved just a scalar situation just for the single x component, right? We solved this just for the x component. And so when we get to this final instantaneous solution, we may prefer to go back to the vector form for the electric field, and the voltage will continue to stay scalar. However, we can still see that the magnitude of this electric field one is the same as the scalar, right? They take the exact same format. And so once again, the transmission line, the plane wave continue to be the same. Now, going back again to that standard waveform that you probably learned phasors on, we can see that there's a bunch of relationships we can now make on the transmission line and on the plane wave related to the frequency and these propagation constants or wave numbers and the reference angle. And these are the main ones that you'll probably see. So we have some information about the propagation velocity for the transmission line. It's equal to L prime C prime, so it's related to the inductance and capacitance of your line. Whereas for the plane wave, we'll say that it's only related to mu and epsilon. And again, we'll keep calling the plane waves wave number k, whereas on the transmission line, you might call it, continue to call it beta. And that both of those, regardless of which one you call it, are related to the frequency. Now, going further, we've just come up with the solution for the voltage and the electric field, but we know that from the beginning we had two wave equations for the transmission line and two for the plane wave. One for voltage, one for current, one for electric field, one for magnetic field. And so we want to be able to derive the current and the magnetic field. For the current, right, we're just going to start over and we'll be able to derive the same thing using the same process. However, for the plane wave, you might prefer to use the perpendicularity from the Faraday equation to figure out what the magnetic field is going to be. And because we derived the electric field, right, for the x, we know that if it's perpendicular on our xy plane wave, where we have a uniform plane wave, the magnetic field is in the y, so they're perpendicular to each other. But we can see that these two are once again going to be very similar, right? So the current and the magnetic field, right, they're going to have that same solution form, just as we expected based on that wave equation that we started with. Now, for the transmission line and the plane wave, we should be kind of clever and realize that the current and the voltage are going to have some relationship, and then the magnetic field and the electric field will also have some kind of relationship. So we want to relate these coefficients to the voltage and electric field versions. And to do that, on the transmission line, you use the telegrapher equation, and in the Maxwell's, or in the plane wave, you're going to go back to Maxwell's equations and use the Faraday equation. By doing that, we can rewrite on the current, we can write it as a function of voltage, and on the magnetic field, we can write it as a function of the electric field. Now that leaves us with some coefficients out front, and what we like to do with these is we like to give them a special name. For the transmission line, we call it the characteristic impedance, and for the plane wave, we call it the intrinsic impedance. So Z0 for the transmission line, and eta for the plane wave. And we have some relationships for the characteristic impedance and the intrinsic impedance, and we can see that they're very similar to each other, right? We have this root of L over C, root of mu over epsilon, and it makes sense because, right, we said that for the TEM case on the transmission line, LC would be equal to mu epsilon. So it's not a surprise that these look so similar. Now, by doing this, we can rewrite our final equation for voltage and current. We can rewrite it, the current one, as just a function of voltage, and we can rewrite the magnetic field one as just a function of this electric field coefficient, and they're related by the characteristic impedance and intrinsic impedance that we just defined. Now, we should note for the transmission line that although we have L prime C prime equal to mu epsilon, we can design transmission lines for quite a few values. 50 or 75 ohms are common ones. However, for plane waves, we note a very special case, which is that when we have relative permittivity and permeability is equal to 1, we get this special intrinsic impedance of free space. Now, for the transmission line and the plane wave, when the dielectric material has the same mu and epsilon equal to 1, the wave propagation speed is going to reduce to the speed of light in both cases. And so now we can see that these two transmission line and plane wave equations are very similar to each other, and there's a lot of parallels that we can draw between them. Now, the last thing I want to note is that when we were deriving these in parallel, for the transmission line, we said, let's talk about a case where we had no reflection, but that's not typical. Typically, right, you do have reflections for transmission lines, and that's why you end up writing them like this, right? So we do include both the forward traveling wave and the reverse traveling wave solution for the transmission line. Whereas for the plane wave, we do still continue to talk about the plane wave as if it's only traveling out to infinity. However, the assumption we made that the electric field would only have the x direction component is not necessarily a very good assumption or simplification, and so we can make a more general case where the electric field has both some x and some y component on the uniform plane wave, and likewise so would the magnetic field. And this leads to two final things which you see a lot. One is that for the transmission line, we then develop this reflection coefficient so that we can eliminate, right? We can eliminate that second coefficient, and we can write it all in terms of reflection coefficient. And for the plane wave, we also like to note that this relationship, we derived this relationship for a xy plane, but we can make it very general to any plane, whether you're on YZ, ZX, and so on. We can make it very general with these two relationships where the electric and magnetic field are related to the curl of the other field, via this k, which k is the direction of propagation. So in our derivation, we assumed that k was equal to z, but this could be anything. This k could be x, it could be y, or it could be something complex, right? It could be x plus y, right? It could be a tilted plane. We don't necessarily know. But as long as you know the direction of propagation or the two of the fields, you could solve for it. So I hope this helps you put together a bunch of pieces that you learned in your electromagnetics class that relate the phasors, they relate this wave equation, they relate the transmission line derivation, they relate the plane wave. I hope that this all helps put it together and helps you see why we like to use phasors, why we solve these wave equations a certain way, why the transmission line and the plane wave when solved in TEM mode look so similar. And there's just a lot of similarities, and I hope that this video helps summarize and kind of cap off probably a lot of what you learned in electromagnetics. Thank you, and see you in the next video.